right? So in the last video we went over how a language is built, what are the different steps generally involved, right? And we looked at this first part, which is called lexer or tokenizer, which basically does lexicon analysis and converts the original source code, right? Original source code meaning something like this, into a series of tokens like this, right? So this thing here, this text, this block of text is being converted into a series of tokens. So now we have this series of tokens, and so now we need to go from this series of tokens into a abstract syntax tree. So basically we will be arranging these tokens into a tree, which will then help us make meaning out of what uh, what needs to be done. So I had no clue how to start, how to get started. So I basically did a whole lot of research on how the parsers are written, how different languages generally handle parsers, and then there's a general opinion that you can either write parsers by hand, or you can either use something like a parser generator, where you pass the grammar rules of your language, and then the tool will generate a parser for you, which can parse the grammar that you originally supplied, right? So there was a lot, and obviously these are trade-offs between both of these strategies. So I kind of did a lot of research to figure out um, uh, what essentially I need to do. What do I write to a parser by hand? If I do write a parser by hand, what kind of parser do I write? What kind of parser will be powerful enough to handle the grammar that I'm going to use? Right? There's a lot of different variations of parsers, but there's generally there are two ways to write a parser, since you will be making a tree, right? So it's a tree data structure, and then you can start building tree from the bottom up, right? So you start with the leaves and go to the root, or you can do the opposite way, where you start with the root and go to the leaves, right? That's how you there are only two ways to generate a tree structure. So I decided to go with a very common and very intuitive way of making a parser, which is called a recursive descent parser. This recursive descent parser is easy to write, and obviously like the name suggests, it has recursion involved in it, and it models your grammar pretty much exactly, right? It models your grammar very well, and you don't have to think about, okay, backtracking, and then there are certain scenarios, right, where you need to look ahead and this and that. So I basically started writing a recursive descent parser. Now to before doing this, I kind of had to formalize my grammar. So what I did was I had written a original specification of the grammar. So if you see here, this is the grammar for the language that we have. We start with a compilation unit, right? Compilation is unit is basically a file. Maybe compilation unit will mean something else when once we get to more complex constructs, right? Like modules and things of that nature. But for now, compilation is a unit is a file, and each file can have blocks. A block is just a statement or a series of statements, right? And it can also be, some blocks can also be indented statements because we are using an indentation based language. Then we have statements, then we have expressions, then in expressions we have different type of we've kind of have to split your expressions into different things, because there's something called precedence that you have to take care of, right? So if you in let me show you this example, right? So here you are doing subtract, and then you're doing multiply, right? So obviously multiply will should happen first, right? So 3 into let's imagine that there were no brackets here, right? So 3 into 4 should take place before before subtracting the result from 20, right? So, and you can obviously change this behavior once you add brackets. So your language should be able to handle scenarios like this. And the thing with recursive decent parser is that they are not very good in handling precedence. That is what, like, one drawback. They also can't handle left recursion. So to handle this, there are to handle operator precedence and associativity in a correct fashion, there are a bunch of different algorithms. Some popular ones are mainly shunting yard. There's the shunting yard algorithm. Then there's operator precedence, there's a precedence climbing algorithm. Then there's a Pratt parsing. So Pratt parsing is an algorithm like devised by Von Pratt, and it's actually called, the formal name of it is top down operator precedence, and this is what we're using essentially to parse our expressions in our language. So if you see, if I go to the source code, we have a separate class, and this separate class is an implementation of the Pratt's parsing algorithm, where you use binding power, and we have binding to basically determine which part of the expression will be calculated first. And so if you see here, we have defined our precedence, and different things have different precedence, right? So the operator having the highest precedence will be able to hold its operands tighter, and this will be calculated first. So that's generally the idea behind Pratt's parsing. So we have an expression parser here, and then we have our normal parser for other things like function definitions, function calls, if else statements. That's all pretty much we are supporting right at the moment. And later down the line, I'll expand this to add more things, right? So the grammar that you see here is not fully implemented at the moment. And the grammar itself is incomplete. All it tells, all it mentions right now is expressions, functions, if else, right, arguments, how those are defined, nothing much. So right now we don't have a concept of classes, we don't have a concept of modules. Later down the line, we'll have to define how these things look in the grammar, and then how to we implement it using our parser, right? So this is the main parser class. And when it comes to expression, by the way, if you notice here, we basically have one function to handle each non-terminal. So block is a non-terminal, statement is a non-terminal, right? So we have a function which handles block, we have a function which handles statement.